In this lesson, we're going to look at solving radical equations. However, we're going to need a new principle to help us. In the last few lessons, we used the zero product principle, A, B equals 0. That principle was a simple result of the properties of multiplication. If the product of two terms equals 0, then at least one of the terms must also be 0. The principle we're going to look at is called the power principle. Let's say we have an equation. Instead of writing all the terms, let's just say the left side is P and the right side is Q. So we have P equals Q. In order for an equation to stay equal, whatever we do to one side, we must do to the other side. So we're going to raise both sides of this equation to a power. Rather than choosing a specific power like squaring or cubing, let's just raise both sides to some arbitrary number n. If you've never seen arbitrary in mathematics before, it basically just means some random legal or appropriate number. So raising both sides, we get p to the n equals q to the n. We've now set up the premise for our property, the power principle. If p and q are algebraic expressions, and n is greater than 0, then every solution of p equals q is a solution of p to the n equals q to the n. Let's take a look at what this says. First, we're given two conditions. P and q are algebraic expressions, such as 3x minus 1 or x squared plus 2x minus 4. It doesn't matter, as long as they're algebraic. Then, we are given that n must be greater than 0. After the conditions, we're given a one-sided statement. It says that any solution we get from p equals q will also be a solution of p to the n equals q to the n. There's a reason we say this is one-sided. Let's look at a simple example. Let's assume we have the equation x equals negative 3. Clearly, there's only one solution, x equals negative 3. But our property says that any solution of p equals q is also a solution of p to the n equals q to the n, indicating that p to the n equals q to the n may have more solutions than p equals q. Let's square both sides of our equation. This simplifies to x squared equals 9. We can take the square root of both sides, revealing two solutions, x equals plus or minus 3. Look at what we have. We have the true solution, x equals negative 3, but also this leftover, x equals positive 3. What do we do with it? There's a special name for these types of solutions. Extraneous solution. Any solution of p to the n equals q to the n that is not a solution of p equals q is called an extraneous solution. Extraneous solutions may be introduced whenever each side of an equation is raised to an even power. All this is saying is that when we raise both sides of an equation to an even power, we may receive solutions that were not present in the original equation before being raised. These solutions are called extraneous, and most of the time, they can be ignored when identified. Now that we have the power principle discussed and the consequences of this principle, let's work some examples to showcase it. Number 1. The square root of 2x plus 5 equals 2. Our first example involves an expression under a square root. Since the square root can be expressed as an expression raised to the 1/2 power, we're going to square both sides to eliminate the radical. This gives us 2x plus 5 equals 4. Simplifying gives us 2x equals negative 1, and the solution x is negative 1/2. In this example, we see that we only got one solution. Not every application of the power principle will yield extraneous solutions. If we plug in our solution into our equation, we get 2 times negative 1/2 plus 5, all under the square root, equals 2. Simplifying, we get negative 2 over 2 plus 5 under the square root equals 2. Going on this side, we get negative 1 plus 5 under the square root equals 2. Square root of 4 equals 2. 2 equals 2. Thus, our solution is correct. Number 2, x equals 1 plus the square root of 1 minus x. Here we have two variables, one of which is under a square root. First, let's get the square root by itself. We get x minus 1 equals the square root of 1 minus x. Now we'll square both sides. This gives us x squared minus 2x plus 1 equals 1 minus x. Simplifying, we get x squared minus x equals 0. We then factor out one of these x's, leaving us with x times x minus 1 equals 0. Using the zero product principle here, we get x equals 0 and x equals 1. Let's see which of these solutions work. First, we'll check x equals 0. Plugging 0 into our original equation, 0 equals 1 plus the square root of 1 minus 0. This becomes 0 equals 1 plus the square root of 1. 0 equals 1 plus 1. 0 does not equal 2. So x is an extraneous solution. Let's check x equals 1. Plugging 1 in, we get 1 equals 1 plus the square root of 1 plus 1. 1 minus 1 becomes 1 equals 1 plus square root of 0. 1 equals 1 plus 0. 1 equals 1. So our only solution is x equals 1. Number 3. The square root of x plus 1 minus the square root of 2x minus 5 equals 1. This equation has two separate square roots. They're not common either, so we can't combine them. Let's first separate them so there's only one on each side. The square root of x plus 1 equals 1 plus the square root of 2x minus 5. Now let's square both sides. This looks difficult, but if we use the formula a plus b squared equals a squared plus 2ab plus b squared, and have a equals 1 and b equals the square root of 2x minus 5, the difficulty vanishes. We get x plus 1 equals 1 plus 2 the square root of 2x minus 5 plus 2x minus 5. Notice there's still a square root present, so we'll need to use the power principle again. But first, let's simplify and get that radical by itself. We get negative x plus 5 equals 2 times the square root of 2x minus 5. Squaring both sides, we get x squared minus 10x plus 25 equals 4 times 2x minus 5. Simplifying a little bit further, we get x squared minus 10x plus 25 equals 8x minus 20. Now we push everything to one side and set the equation equal to 0. This gives us x squared minus 18x plus 45 equals 0. Now we have a quadratic equation with some large looking numbers. But 45 is a fairly easy number to factor. I like to think of a clock. 3 times 15 is 45, and negative 3 plus negative 15 is equal to negative 18. So let's factor this quadratic using those factors. We get x minus 3 times x minus 15 equals 0. This product implies that x equals 3 or x equals 15. Let's check x equals 3. First, plugging 3 in, we get square root of 3 plus 1 minus the square root of 2 times 3 minus 5 equals 1. We get the square root of 4 minus the square root of 6 minus 5 is 1 equals 1. This becomes 2 minus 1 equals 1. 1 equals 1. So x equals 3 is a solution. It's likely that x equals 15 is not a solution, but we still need to check that x equals 3 is the only solution. So check for x equals 15. Plugging 15 in, we get the square root of 15 plus 1 minus the square root of 2 times 15 minus 5 equals 1. Simplifying, we get the square root of 16 minus, we got 30 minus 5, the square root of 25 equals 1. That's 4 minus 5 equals 1. Negative 1 does not equal 1. So x equals 15 is an extraneous solution, and x equals 3 is our only solution. Number 4. The cube root of 2x squared plus 5x minus 3 equals the cube root of x squared plus 3. One last example. Notice that these roots are cube roots, which have the exponential form of p raised to the 1/3 power. So we're going to cube each side of this equation. This gives us 2x squared plus 5x minus 3 equals x squared plus 3. Simplifying and setting the equation equal to 0, we get x squared plus 5x minus 6 equals 0. Factoring this quadratic, we get x minus 1 times x plus 6 equals 0. This gives us the solutions of x equals 1 and x equals negative 6. Let's first check for x equals 1. Plugging 1 in, we get 2 times 1 squared plus 5 times 1 minus 3 under the cube root equals the cube root of 1 squared plus 3. We're left with the cube root of 2 plus 5 minus 3 equals the cube root of 4. Simplifying a little more, we got the cube root of 4 equals the cube root of 4. This here is simplified enough. Anything more would produce approximations. So x equals 1 is our solution. Now we'll check for x equals negative 6. We get the cube root of 2 times negative 6 squared plus 5 times negative 6 minus 3 equals the cube root of negative 6 squared plus 3. Simplifying, we get 2 times 36 minus 30 minus 3 equals the cube root of 36 plus 3. Let's continue simplifying. We get the cube root of 72 minus 33 equals the cube root of 39. One final simplification. 72 minus 33 is 39. So we got the cube root of 39 equals the cube root of 39. Wait, look at this. Both solutions are acceptable. This is because extraneous solutions may only arise when we raise both sides of an equation to an even integer. Since we raise this equation to an odd power, 3 in this case, all solutions obtained would be true. So there's really no need to check when we raise equations to powers of odd numbers. This lesson was a bit long. It was originally going to be longer, but I feel that it would be better to split it into 2 separate lessons. In the next lesson, we'll finish up radical equations. More specifically, we'll talk about equations containing variables with rational exponents.